Hi guys, welcome to our second projectile motion video. Now today we're going to be going through the projectile motion equations and how to do the calculations. So it's a bit intense, so make sure that you pause it whenever you need to, or re-watch any parts that you need to clarify. So there's a general approach that we need to have, and we went through this when we were having a look at vectors. So we consider projectile motion as the sum of two individual independent motions. So one of the motions is in the horizontal direction and one is in the vertical direction. Now, because both of these are linear motions and because acceleration is constant, we can use Newton's equations of motion. So here we go, here's Newton, and we have a heap of his equations of motion that we can use to help us with these problems. So the acceleration in the horizontal direction, we talked about this last video, that's 0 because there's only one thing acting on a body in this direction, and that's gravity. So it's moving with a constant velocity, and the only calculation possible for this direction is given by s is equal to vt, or the displacement is equal to the velocity times time. Now, when we look at projectile motion problems, we need to decide whether or not we are going to use h to represent horizontal, or if we want to use x as in terms of the x direction. So if we do either of those, we need to apply it to the whole of the equation. Now, this equation is mainly used to determine the range of a projectile. So if a question is asking you how far has the object travelled, then this was the one to use for range. Now, in the vertical direction, a body is subject to constant acceleration, or it will be affected by gravity. So gravity is 9.8 meters per second squared, or negative 9.8 meters per second squared, depending on which one we're going to be talking about. So normally we take up to be the positive direction, but it's entirely up to you. My word of advice is to make sure that you specify that when you're answering a question, so you just write a little note, up is negative 9.8 or up is positive 9.8. Now, the three relevant equations here are, the first one is v is equal to u plus at. So that to find the velocity, it's the initial velocity plus acceleration times time. And the second one here is displacement is equal to the initial velocity times time plus half of acceleration times time squared. And the third one is v squared minus u squared equals 2as, or velocity squared equals initial velocity squared is equal to 2 times acceleration times the displacement. Now, as long as you have those written down, you'll be able to figure out which one you need to use depending on what information they've given you in the question. And we'll be able to cover that a lot in some examples so that you can see how they're applied. Now remember, if we're looking at a projectile motion problem, it's going to make sure that we're looking at either the v's for vertical or y's for vertical. So that first equation becomes v of v or u of v plus gt, and g would say for gravity instead of acceleration, because in this vertical realm, I guess, our acceleration is provided by gravity. And you can see here, instead of the little v's, we've substituted in y. So it's entirely up to you what you feel more comfortable using, whether you want v's in your equations or y's, or h's and x's as before when we're talking about things in the x direction or in the horizontal. So entirely up to you. These do look more complicated than they actually are. Alright, these are the same three equations up here, and we've just substituted in v's or y's so that you know exactly which components you need to add in, because it makes it less confusing and you actually realize which number needs to go where. So I suggest doing this when you're writing your equations because it will help. Okay. Now this first relationship, the first equation there, is used to calculate the vertical component of velocity at any time and the time of flight of the projectile. So if someone's asked you to calculate a kicking ball type question and they've said what is the time of flight of the ball, then that one will be really handy. The second one is usually used to calculate the time of flight as well, and they can calculate the same thing, but you may be given different information in question. So you'll need to apply the one that you have the information for. And the third one is the most straightforward way of calculating the maximum height. So if someone's kicked a ball, what is the maximum height the ball will achieve during its flight? And this is the most straightforward way of calculating that one. Okay, so just a reminder that S is displacement and it's measured in meters. V stands for velocity and it's measured in meters per second. U is the initial velocity, also in meters per second. Time must be in seconds. And G is acceleration due to gravity, which is 9.8 meters per second squared. Alright, so you're going to face two types of problems when we're looking at projectile motion. The first one is horizontal projection, which is something being pushed off of something or pushed out of something. And basically some examples of this is a ball rolling off a table, supplies out of an aeroplane is a good one that people like to use in exam questions, a stone being thrown off a cliff, or pushing someone off of a cliff, or a car plunging off a cliff, something like that. Basically, because there's only one direction that the projectile is going, then we can say that downward direction is said to be positive in terms of our application of gravity. So 9.81 would be positive because it's not going up and down, it's just going down, so there's no point in making it negative. It can all just be positive. Because again, in this circumstance, negative and positive is just talking about a direction. It doesn't have anything to do with the magnitude. The other type of question we might get is called a unilevel angular projection. So basically, when something is on the ground and kicking a ball or something and then returning to the same height on the ground. So an example of this type might be a high jump, or a golfer, or a cricketer, or, as I said, a footy player, or something like that. And because we have two directions, so the ball will go up and then down, usually we take the upward direction to be positive and then the downward direction to be negative. This is a good way of having some steps, I guess, to work out, to problem solve these types of issues. So the first one for projectile, so horizontal projection, step one, because all the vertical motion is in the downward direction, we have to call this positive, so we have to assign the direction. Step two is we establish all the initial conditions, so write down everything that we know. Alright, so 9.81 is gravity, and that goes in the y direction. Initial is 0, okay, because it doesn't have any initial motion in the y direction. Its initial motion is getting pushed in the x direction. Time of flight we can work out using our equation of motion that we have there, and u of y, okay, is 0 because it doesn't have any motion in that downward direction. So that whole term here becomes 0. So s of y, which is the displacement, okay, works out to be just this second part. S of y is equal to half a t squared, and then we're given a height, which is our s, and we can rearrange to get t for time of flight. If we're wanting to get range, we use our range calculation. And notice how now instead of y's, this one has x's, because range, we're talking about a distance in the x direction. It's going across. So remember, we're always thinking of these things independently for projectile motion questions. To find the velocity at any time, we can use this equation here. And again, u in the y direction, so u in the vertical is going to be 0 because there was none. All of our u was in the across or in the x direction. I can give you these on a piece of paper if you would like. It might make it easier. Otherwise, feel free to copy it down. It's just a handy thing to have. The other type of question, so unilevel projection, the same thing applies, so the same steps. So the first one is to assign whether or not we're talking about gravity being positive or negative. And again, writing down all of the conditions that we have, finding our initial components of x and y, which we practiced the other day, And then this is very handy to know. So by the symmetry of this motion, so it being a parabola, the time of flight is twice the time taken to reach its highest point on the trajectory. So once it hits its turning point, it doubles that motion for the other side of the parabola. So at maximum height, the vertical component of velocity is 0 because it stops, and then we can, at this time, we can find that by working out, if we substitute Vy equals 0 into that equation, we can find what that time would be, and then double it to get the time of flight. Maximum height, we can substitute in into this formula here, alright, with the t time to get to its maximum height that we've just found, or we can substitute it into this one. The range and velocities are found in the same way as the other case, and because of the parabolic motion, in the case of unilevel projection or a cricketer or something like that, the final speed is actually the same as the initial speed, because remember, we don't worry about air resistance in this course, so there's going to be nothing that impacts it. So the final velocity has exactly the same direction below the horizontal as the initial velocity had above. So for example, a cricketer hits a ball to a fielder or a boundary or something and hits it at 30 degrees with a velocity of 12 meters a second, and it's going to hit the ground with a velocity of 12 meters per second at 30 degrees the opposite way. So it's quite simple because it is that parabolic nature. Okay, I'm going to show you some examples, and I found the textbook would have these fairly well laid out, so I'll just go through this one with you. So horizontal projection is the first example, and then we go through a unilevel one. So an aeroplane is dropping a parcel of medical supplies to a boat at sea. The aeroplane is flying horizontally at a height of 240 meters above sea level with a speed of 90 meters a second, and we have to calculate the time between the parcel leaving the aeroplane and hitting the water, so the time of flight. We also have to find how far the boat and how far from the boat the aeroplane must release the parcel, so the range, and also the final velocity of the parcel. So firstly, in horizontal projection, because the vertical motion is at all times in the downward direction, so we only have one part of the motion, we call that positive. So all the vectors will be positive. We have acceleration in the y, 9.8, in u in the x direction, so initial velocity in the x direction is its speed, so 90 meters per second, and u in the y direction is going to be 0 because all of that initial velocity was in the x direction. So from that we can say the parcel hits the water when it has dropped 240 meters, so when s in the y direction equals 240. So that's exactly the same time as it takes a body dropped from the same height to fall 240 meters vertically. So if we substitute this into our s equals ut plus half at squared equation, this whole component here, uy times t, is 0 because there was no initial component of u that was in the y direction, so that's 0. So it becomes half times 9.8 t squared. We can rearrange that and then transpose it, get t by itself and square root that answer, and it gives us a time of 7 seconds. Second, so range. When we want to try and find the range of the parcel, the easiest one to do is to try and find the s of x is equal to vx times t, or s equals bt. Now v of x is equal to u of x because there's only one component of that initial velocity, and it's going to be constant right throughout that that journey because there's nothing else acting in that in the x direction. So it becomes 90 times our 7 seconds, which equals 630 meters. So the range of that projectile is going to be 630 meters. Okay. So finally for that question we then have to calculate the final velocity. So what I find handy to do here is to actually draw a diagram of what it will look like when it hits the ground. So we're trying to find this v here. Now this v is also going to have a vertical component and a horizontal component, and this is going to be your final one. So what we know is that our v in the x direction over for our final component of velocity is going to be exactly the same as what it was to start with, because there's nothing else acting on that object in that direction. So v of x, or our final velocity, the x component of our final velocity, is going to be whatever it was when it was kicked out of the plane. When our plane was traveling, because that's going to be exactly the same as our plane's velocity. So all we're trying to find then here is our v in the y direction, because we know what our u is. We just need to find this one so that we can then find our final velocity here. So here we use the v equals u plus at, and again we know that u in the y direction, this part is equal to 0 because there wasn't any initial velocity in the y direction. So it just becomes 9.8 times our time of flight, which was 7. So it ends up with 68.6 meters per second is our v of y. Then we can use Pythagoras to rearrange and find our final velocity, which we get as 113 meters per second. So this is 113 meters per second, but velocity is a vector, so we need to have an angle or a direction that it's coming from. So because now we have don't know this angle, alright, and when we don't know an angle, we have to do an inverse function, and because we have Vy and Vx, what we can do then is put that's opposite and adjacent. So opposite and adjacent would be a tan function. So to find tan of theta, it's going to be so inverse tan of 68.6 over 90, which would give us so that gives us 0.7622, and the inverse tan of that would give us an angle of 37.3. So it's always handy to sum up the problem by saying your final answer. So therefore the body hits the water with a velocity of 113 meters a second at an angle of 37.3 below the horizontal. In most situations when you're finding a final velocity, you will be doing an inverse tan to find the angle, because all of the questions end up being very similar, and so it's handy to know that they'll usually be tan. Okay, the second example we have is our unilevel projection, and as you can see, this is the one that's the parabolic in nature. So we can see that this angle here automatically will equal this angle here, because of the symmetry involved in a parabola. Okay, so they're talking about a cricketer here. So a cricketer fielding in the outfield throws the ball to a wicketkeeper with a speed of 25 meters a second at an angle of 30 degrees above the horizontal. The wicketkeeper catches the ball at the same level at which it was originally thrown. So again, we have to find 1, the time of flight, 2, the distance the fielder from the wicketkeeper, i.e. that's the range, the velocity at which the ball strikes the wicketkeeper's gloves, so that's your final velocity, and this time they're also asking us to find the maximum height that is reached by the ball. So the first thing is to break our initial velocity, our u, into its components. So first of all, u of x is our cos function, and u of y is our sine function, and we get these two components of our velocity here. So we have to assign our gravity. So in this example, vertical motion has two directions, up and down. We take upwards direction to be positive and downwards to be negative. So therefore, acceleration in the y is going to be negative 9.8 meters a second. So anything going down is going to be like negative. So time to reach the height. So what we want to find here is what we're talking about before. The time to reach maximum height is here. And it's easy to find that because that's going to be when our u in the y direction, So when it's up here, it's going to be going 0. Because it's reached its turning point, it goes up, and then it stops, and then it comes down. So when that is 0, we can find the time to reach that point, and then because of the shape being parabolic in nature, we can just double that to get the time of flight for the whole thing. So here we use the equation v equals u plus at, but this time all in the y direction, and we put in our 12.5 and our gravity, and we can rearrange that to get time, which we get as 1.2755 seconds. So therefore the whole time, because that's only to get halfway, is going to be 2.55 seconds. Range, remember our range formula was s equals vt, so we know that in the x direction, v of x is going to equal whatever u of x was. So our initial component in the x direction was up here, so 21.65, and remember that it's going to be the same u of x the entire way. There's nothing else acting on it in that direction, so even our final component, our u of x will still be the same. So we put that in there, so our final velocity, or in the x direction, is going to be the same. So 21.65, and our time, 2.55. We had a range of 55.2 meters, so the distance between the wicketkeeper and the fielder is 55.2 meters. When we want to find our final component of velocity, we find it exactly the same way. We draw our little diagram. We find our v of y, because we know our v in the x direction, it's going to be what it was before, so that one is going to be, what was it? I think it was 21.65. Here we know u of y is going to be, u of y is 12.5. That's from our initial calculations. A is our gravity, and t is our time of flight, so 2.5, and that gives us a v in the y direction of negative 12.5, which makes sense because it's the opposite of when it went up. We want to find the final component of velocity here, so the same thing, we do our Pythagoras, put in our two known sides, and rearrange to find v, and we get 25 meters a second. And then we can do our inverse tan function of our vx and vy, and we get an angle of 30 degrees. Excellent. So what we can see there is it's exactly the same as when it left. So if you were clever and you could say by symmetry, then the velocity and the angle is going to be the same, and that would be a perfectly acceptable exam answer. Now lastly, to find the maximum height, so when v of y equals 0, so that's what we want to find, so that's the turning point. When that ball stops, what height does that occur at? So we want to know when v of y equals 0, so put in 0 here, put in all the rest of it, and we can rearrange to try and find our s, so that at what height does that occur. So we rearrange that, and we get a height of 7.97 meters. So if those of you need some rearranging practice, projectile motion equations definitely will provide you with that practice. So there are some additional sources there. If you are still struggling, there is a heap of them. Make sure that you check them out if you do want any extra help. Otherwise we'll go through a heap of problems in class. Alright, I hope you took your notes and write down any questions that you have for me. I'll see you soon.